Hey class, we're going over chapter 4.5 today, which is also undetermined coefficients. This time, however, we are going to use the annihilator approach. So there are two approaches to this method. Last video, we went over the superposition principle, the superposition method. So now we are doing the annihilator method. Okay, so in this section, we will, of course, again use undetermined coefficients method, but not by guessing the form of our particular solution. Okay, this time what we're going to do is we're going to use the differential operator, d of y, where y is some function in x, to annihilate our g of x function. So let's see what we mean about this, what we mean by this to annihilate a function. Okay, so let's start with the easiest, which are generally polynomials. Okay, so if we have a polynomial of degree n minus 1 or lower, the annihilator function d of n will annihilate that polynomial. Okay, so think about this as us basically taking the nth derivative. So the differential operator, we talked about this in class briefly. This differentiates my function y. So if I take the nth derivative of a polynomial that has degree n minus 1, my polynomial will disappear, right? So if I have a quadratic, a second degree polynomial, if I differentiate it 3 times, it goes to 0, right? That's basically what this is saying. Let's do an example. Let's say I want to use the differential operator on this function. Okay, d sub y, here this y is y equals 2x cubed plus x squared plus 1. So if I do one differential operator on this, I get 6x squared plus 2x. So when I differentiate this, this is what I get. If I differentiate it twice, right, this is me doing the differential operator on this once and then doing it twice. So you can think of this as the differential of the differential, right? So if I do this twice, I'm basically differentiating this function, so we get 12x plus 2. If I do it 3 times, I get just this coefficient, this constant term 12. And of course, since this was a cubic, the fourth derivative will annihilate the entire function and get me 0. Okay, so what we're going to do is we're going to look at some of the forms of the differential operators that annihilate our common functions. Okay, so here d4 annihilates this function. So in general, we can have the following, right? So we'll put our operators over here and the functions that they annihilate over here on the right. So d to the nth order differentiates or annihilates, I should say, a polynomial of degree n minus 1, right? So, or lower, anything that's up to the n minus 1 power. D minus a annihilates e to the ax. So just think about section 4.3 where we were making those auxiliary equations, right? So if we just think about, instead of substituting y prime as m and we substitute y prime as d, well, when I had the m minus a, that solution looked like this as a function for the solution in that general solution, right? So it makes sense that instead of m minus a, I'm just using d's instead of m's, really, right? That's what's going on. So m minus a has a solution of a, so that looks like this. This is the function that it annihilates, okay? So d minus a to the n, it's this very similar to, again, when we had those auxiliary equations. If I have more than one, well, for instance, if I had if I had m minus 2, the first one would be e to the 2x, and the next one would have to be linearly independent from the first, so I'd multiply it by a higher power of x. If I had a third one, I would multiply that times x squared. If I had a fourth one, I would multiply that by x cubed. So that's what this is saying. It's just extending this idea that we've already been playing with, and we're just writing it in terms of factors, okay? if I have a polynomial that looks like this in my D equation, this is pretty much the form of a quadratic that has complex solutions, right? So we're just saying that A from your complex answer and beta from your complex answer in your quadratic look like this. So if we have a polynomial that has this kind of form, this is the solutions that we would have gotten out from that auxiliary equation. So this as a differential operator annihilates these set of functions. Okay, so there's two, this kind and this kind, right? If we extend that a little bit more, basically assuming that alpha is 0, so it's just an imaginary root and not a complex root, or I'm sorry, let's step this up to the nth power. Okay, then we have the x to the n minus 1 function factoring in also, and then if we take out the alpha and we have just an imaginary root, then we get the cosine beta and sine beta as well. Okay, so these I actually like this method a little bit better than the superposition approach, because superposition you had to remember multiple kind of forms. Here it's really easy. You're really just kind of forming polynomials, right? So let's go over these steps. One is I want to substitute each derivative with its differential operator analog in YG. Okay, so what do I mean by that? Just like we form the auxiliary equations with m squared plus m plus what have you, we're going to do the exact same thing but with the differential operators. Okay, so basically we're looking at the differential operator equation that will annihilate that general solution. Okay, so well, I don't have an example yet. We'll talk about this. Okay, so solve the auxiliary differential operator equation. So again, basically what I did in step 1 was I formed an auxiliary equation, but instead of m's, I used d's. Okay, so in number 2, I would find the roots to that equation, that polynomial I formed. And then after I did that for the general portion, the homogeneous equation, I'll do that again for the g of x portion of the non-homogeneous equation. So I'm doing it twice. I'm doing it for the homogeneous part and the g of x that makes it non-homogeneous. Okay. So note here that my g of x can be several functions being added together, but when I'm forming my operators, my annihilator operators actually multiply for when I'm annihilating each of the YPIs, I guess you would say, for g of x. Okay, so 4 is I'm going to form y of p based on the solutions to the differential operator equation that I used to annihilate g of x. 5 is I'm going to differentiate my different y sub p's, or my single one that's made of several pieces, so that I can substitute it into my differential equation. So really a lot of what we're going to do is very similar to what we did in 4.4. Okay, after I take all those derivatives and I substitute it into my equation and I simplify everything down, I set what I have equals to my g of x function, and I just make a system of equations based on the coefficients. Okay, so a thing of note, this is mostly what I'm going to do here, is we can simplify this really down to like 4 steps, because steps 1 and 3 can be done at the same time, so that we annihilate the entire equation at once instead of the homogeneous part and solve it, and then the non-homogeneous part and then solve it. We can just annihilate the entire equation and find all of my roots at once. That'll generally be a little bit easier. The only thing is we have to keep track of which roots go with the homogeneous portion and which roots go with the non-homogeneous portion, and that's not easy. Or, I'm sorry, that is easy. You just have to stay organized. Okay, as long as you're not mixing things up, you should be fine. Okay, so let's do an example. Right, it's always easier to do an example than to look through a wall of text. So we have this second order equation, and I have a non-homogeneous equation because I have a g of x function. So what I want to do is I want to basically solve and think about what annihilates this, and for the homogeneous portion, my y double prime will just turn into a d squared. This will turn into a d. There is no equation for this portion. And then I'm just thinking about what annihilates these. So we know it's d minus whatever that root is. And for this, it's a polynomial because this is a form of a polynomial. So if you notice, this is also very similar to the form of the g of x we had in our last example in the video that we had for 4.4. Okay, but this homogeneous portion is different. It's not the same equation. So let's say we want to annihilate the entire equation at once. I feel like this is an easier thing to do. So if I annihilate this whole thing, I just get one polynomial that equals 0, and I just keep the two portions kind of separate, right? So in order to annihilate this, I get the d squared, the 6d, right? Because that is the differential. Here, there's no differential for this part, so we just add plus 8. So I get this polynomial equation. So this is going to annihilate that first part, okay? This, d plus 2, is going to annihilate this portion, right? Because this annihilates e to the x's. So if we go back a couple steps, a couple slides, I guess, right? We're looking at this general form, okay? D minus a annihilates things like this. D will annihilate just a single polynomial. And then for the homogeneous portion, we're just substituting our y primes and our y prime, double primes. Okay. So that annihilates this. And if I want to annihilate this, it's basically a linear equation, right? Or a polynomial of degree 1. So in order to get it to annihilate, to go away, I need to differentiate it twice, right? If I differentiate it once, it goes to 2. If I differentiate it twice, it goes to 0. So I need a d2. So if you notice, if I put all these things together, this annihilates that, this annihilates that, this annihilates that. So when I have this whole equation together, I will get out 0 because I annihilated my entire dE, right? So now I'm going to solve this, and the roots to this is what is going to be the form of my solution, right? So it's much easier because I'm just turning this whole thing into a polynomial. Okay, so again, remember, yes, these things are being added, but the way my operators work is that when they multiply, they're taking care of each individual function, right? The functions are being added, so I multiply the operators to get rid of everything. Okay, so this gets rid of this, this gets rid of this side, and this gets rid of this one. So all together, I will have 0, right? So of course I want to find the roots for everything, so I can factor this, right? So I have d plus 2, d plus 4, d plus 2, d squared. Notice I have d plus 2 twice, but for right now, I'm going to keep them separate because this annihilates the homogeneous and this annihilates the non-homogeneous. So for right now, I'll keep them separate, okay? And again, we can group those together. So the homogeneous portion is annihilated here, and this annihilates the non-homogeneous, okay? If I do throw them all together, I get what looks like this, okay? D squared, d plus 2 squared, d plus 4. So we have some repeated roots. Remember, when you repeat roots, they start to bump up times x, right? Times x squared, times x cubed, times etc., right? So my roots are, for the homogeneous portion, this portion, -2, -4, okay? And for the homogeneous portion, -2, 0, and 0, okay? Because there's 2 here for the zeros. So if I start to put these together, okay, my solution for YG, the general solution for the for the homogeneous, is C1 e to the -2x from this one, and C2 e to the -4x from this one. So this one will give me another e to the -2x, but it's a repeated root, so it'll be a C3x e -2x for this one, and then these ones will start to also increase, right? So I have a C3 from 0, a C4x from the second 0, and C5 times x e to the -x because I have a repeated root there, okay? this is the general form of my non-homogeneous solution, and this is the general form for my homogeneous. So my general solution, particular solution. Notice there's no multiplicities going on here. Okay, we don't have to worry about that because I'm taking care of it as I build my solution from the multiplicity in the roots, right? So I don't have to say, I should never say, oh, I have one of these over here already. It's already taken care of as I form my solution, right? So that's another good thing about this. I don't have to multiply by anything to get rid of the multiplicity because I have all of the roots I need to form my generals, or to form the form of my solution for this. So it takes care of itself, right? So I have this as my particular solution. Okay, so my general solution, my particular solution. Again, remember, my particular solution should not have coefficients that are unknown in it. It is a particular solution for this particular equation. As these numbers change, so will the coefficients change, right? So I'm going to solve this by taking yp and finding all of those derivatives I need to plug it into here, just like we did before with the other undetermined coefficients method. Okay, so this is really just another method for finding the particular form. You can use either one. They both work equally well. It's really up to you at this point, which one do you prefer, right? I know you learned the other one first, so maybe you like that, but honestly, I think this one is a little bit easier because it's just all about finding roots and zeros and not memorizing a bunch of forms, right? So I need yp. I'm going to find the first derivative, and I need to find up to the second derivative, right? So I differentiate, C3 goes away, C4 is a constant, and then I have the product rule. And then C4 goes away, this gets differentiated, and I got the product rule one more time. Okay, so I'll just give you guys a second so you can write this stuff down, because I know you are taking notes as you watch this video. So I'm going to try not to go too fast. Now that I have all of my pieces, right, my second derivative, my first derivative, and my p, my particular solution form, I can plug that into my equation, right? Y prime plus 6y prime plus 8y. Okay. So simplify a little bit. So if I substitute all of that into my equation, then I will have my y double prime, okay, is just here. So negative 4c5e negative 2x, 4c5x e negative 2x squared once I simplify, and then 6 times my y prime. Okay, so I just took all the terms and I multiplied them by 6, and I will add plus 8 times my yp here. Okay, so I'm just plugging my things in, and then of course now I want to simplify all of my like terms. I want to combine things as much as possible, right? So I have a constant term here, a constant term here. I have c5e to negative 2x, c5e to negative 2x, and I have c5xe negative 2x's here that get to combine. So they combine down to this form. So I have my two constants, my one single term that has just the x, and then if I combine all of my values that have e to negative 2x's, I get here, and all the xe negative 2x's cancel, right? I got 4 and 8 is 12, minus 12, they go away, right? So if you notice, hopefully you kind of notice this, but our form here generally should take on a very, very similar form to what my solution looks like for g of x, right? So my equation implies that this answer I got is equal to my g of x. Okay, so I just set them equal to each other, and then I can start equating coefficients. If you notice 8c3 and 6c4, those constants, they don't show up over here at all, so that has to add to 0. This is the x term. 8c4 has to be 2, and 2c5 has to be 3 because those are the ones that go together. Okay, so we'll set that up as a system of equations. Right, here we have our first one. That's nice, but it's not really going to help us yet. Okay, I do have 8c4 is 2, and it shows up in this equation. So from the x's here, so that means that c4 has to be 1/4. I'm sorry, and I can use that result now to go all the way back into here to talk about my c3. So let's do that. Okay, so this value implies when I plug it in here that I have 8c3 plus 6 times that c4 has to be 0. So I can now solve for c3. So I can simplify this. 6/4 is the same as 3/2. So I would minus 3/2 and divide all of that by 8. Right? So minus 3/2 times 1/8 or divided by 8 is the same thing. So that's a -3/16. Right? So that's my c3. So I got c4, I have c3, c3, c4, c4, c5 is the last one, and that's easy because straight away 2c5 is equal to 3. Right? So solve for c5 and we got 3/2. So now I have all my coefficients, c3, c4, c5. Right? So I have all of these terms here. c3 is -3/16. c4 is 1/4, c5 is 3/2, and I can use that with my particular solution here. Right? Remember, this is what my answer looks like. I needed c3, c4, c5, so I'm going to take my particular solution. Okay, that should have just been 1. So my particular solution here. Okay, so I got my general form plus my particular solution. So this is going to imply that I have my general solution and then the coefficients where they need to go, right, for the particular solution. Okay, and that's my answer. That's how we do the annihilator approach. So the last 3/4 of it, only 1/4 of this is different, which is that differential operator. The rest of this is identical to the superposition approach. All right, so last video I gave you guys an extra credit problem. I'm not going to do that for every video because that's a lot of extra credit. I will, however, make these problems worth extra credit every so often, but for this video it's going to be worth regular credit. Consider this, again, classwork, right? I wouldn't give you extra credit for classwork, but I do want you to still write down your work, show all of your work on a piece of paper and submit it. Maybe I'll even do half regular credit, half extra credit, right? So 10-point problem, or 5 points of regular credit, 5 points of extra credit, right? Who knows? We'll see. I'm going to go back and forth between it. But the equation that I have for you, the classwork problem, is I want you to solve this boundary value problem. Y double prime plus 4y is 5 cosine x plus 3 sine x, such that we have these conditions being handled. So again, for these classwork extra credit problems, I'm going to be posting the solutions. So that's why I want you to do it, so you have some practice and then you can kind of look at what the actual solutions are. So just keep on trucking along, you guys. I'm glad that you're being patient and staying in the class at this moment. All right, thank you. Bye.